Okay, good morning. And what we have for you today is the continuation of our discussion in electric potential and potential energy. All right. And from what we have from last time, I think you kind of like got an idea of what is the definition of electric potential and electric potential energy and how closely connected they are in terms of like it's the same sense of force and the field. Whenever you see the field, you can get to the force by just multiplying by the q, the charge. Same thing with the potential and potential energy, because we defined the potential to be just the potential energy per unit charge. So that means if you somehow get an information about the potential, multiply that with the charge, you should get back to the energy. All right. But the funny business and stuff like that, stuff that has to sort of like keep in the back of your mind all the time is usually when you talk about potential or potential energy, it means difference. So that means it's always been the between one point to another point, or initial point to final point one to point two, on and on. All right. So that's has to be sort of like kept in mind at all time. Okay, cool. All right. So I think in terms of the attacking the problems, I classified the problems into two types. One type is you are given the electric fields already, yeah, and then you just try to figure out the potential from those fields. Or the other type is you have arrangements of point charges, just like what we did last time over here. Okay. So if this is the case that we are looking at like a distribution of point charges, you usually use this equation right here, KQ over R. That's it. That's what you need. Okay. And by using this, you always have to pair with this clause over here saying potential is zero at infinity. It will pop up like all the time. All right. And if you are given the field, yeah, okay, let me trace by here. Okay, if you are given like an electric field, now you have a sense of what the relationship between the field and the potential is. The relationship is pretty easy. If you go along the field, you are going in the direction that you're moving to a you're moving toward the lower portion of the electric potential. Does that make sense? All right. So it means if you go along the field, you are going in the direction that you are going toward the lower potential. So if you want to go a higher potential, you have to go uphill. You have to go up the electric field directions, just like gravity. Yeah, gravity is pointing down. So if you go against the gravity, that means you're going up higher in potential energy. Okay. All right, guys. So I think that's give you like a quick sort of like a verbal conclusions of what we have done, but I think maybe it's easier just to take a look at examples. Otherwise, we just me talking. Like, no, what I don't know what's going on here. Yeah. All right, guys. So let's get going. Oh, I just forgot to turn the music is still on. Okay. All right. So let's get going, guys.
Okay.
Let's take a look at this example. It's gonna look almost the same as the previous one that we just did last lecture, but let's do this one more time and use this one as a review. So the figure shows a rectangular array of charged particles and it's fixed in place. So we assume everything is static, no movement of charges whatsoever. The distance A is given to be 50 centimeter, and the charges shown is integer multiples of Q1, okay, Q2. So Q1, Q2 are given, and then you are given all the charges as a multiple of Q1 or Q2. Now, let's give potential to be zero at infinity. So anytime that you see this line over here, that's kind of nice because that means that is a ticket for you to be able to use V equal to KQ over R. Nice. Very good.
Okay.
What is the net electric potential at the rectangle's center? So it's the same question as before, except now your geometry is not sort of like as symmetric as before, but the concept stays the same. So let me sort of give you like some drawing over here to locate the center. All right. So let me call that center point to be point P. What you want to do is you want to figure out the contributions of the electric potential from those 6 charges, right? But then we already learned from the previous exercise that if the charges are located at the same distance, all you need to do is you're going to get the same common factor that you can pull out from your summation. So that means you can just do them all together at once by taking the sum of the charge. Does that make sense to you? All right, just to amplify that part, look at this plus 2q on the upper left corner. It will give you a little bit of potential at point P, kq over r, there's no big deal. Same thing will happen to the negative 3q1 on the upper right corner. That will give you also a contribution of kq over r. Now you go to the bottom corner on the left and the bottom corner on the right. Same thing will happen. So there are 4 charges that staying at the same distance from point P. So they're all going to be able to contribute the same, not the same amount, but I mean the same formula that you use to calculate the potential from these 4 will look exactly the same. All right. So you say potential at point P total, let me put the sum of V at P, is going to be equal to, you start from the upper left, K, the plus 2Q1, don't forget the sign, divided by, now let me call this diagonal the D for now. We can figure out the D very easily from Pythagorean theorem, all right? But for now, let me call it over D. And then you keep doing for the next corner, K minus 3Q1 over Q over D. On and on, right? And at the 2 more. But then what I'm saying over here is you can pull out a common factor, K over D, and all you need is just the sum of all those 4 charges at the corner. With me, guys? So far, yep. There you go. Cool. All right, that makes things a little bit easier in conclusion, because what you can see is just you say plus 2 minus 3. Oh, it's gone. Once again.
Okay.
That's kind of nice. Okay, so that means the contributions from 4 charges at the corner give you net 0 potential at point P. But then that's not all. You still have to add the contribution from the side. So you have 2 more charges over here. And now you can see I'm probably not going to get cancellation at the time because they're both positive 4 of Q2. Okay, so what I can do over here is I can add K over A. Yeah, because the distance from those charges to point P are just K over A. And then you do the same thing. I can just do the summation of these charges. So it's going to be 4Q2 plus 4Q2. Yeah. So let me put on underneath here too. So K over A is going to be plus 4Q2. I don't know why I just do this one again. All right. Up here, I'm supposed to put them like one by one, but I know what you get. I think you know what I'm trying to get to. Okay, so I shouldn't put the equal sign over here. Let me just say this is just an arrow. Okay, so this whole summation give you 0. All right, guys. So net. So this term is gone. You only have left with just 2 charges on the side. So that means it's going to be K over A, and then you have 8Q2. And as you can see, good thing about this one is you don't even have to evaluate that diagonal length, because luckily, the contribution from those corners give you 0 net potential. So you can just get rid of all those. So final answer will be 8. You can substitute K if you like, 9 times 10 to the 9. Let me omit the units here. Q2, and it's positive. So you're supposed to actually put positive sign all along. Just want to make sure that, okay, potential over here is above 0. So the potential, the charge over here is 4 times the Q2. Q2 is already given to be 6 pico. Pico is 10 to the negative 12 coulomb. There you go. Divided by the A. The A is given to be 50 centimeter. So I can put 0.5 meter there. And that's it, guys. You are done.
Okay.
See, not too bad. I hope. So the calculation of potential from distribution of point charges is pretty straightforward in the sense that you just do the KQ over R, KQ over R, KQ over R, and sum them all. No directions, no vector summation. Good. Make it very easy to do, except make sure that you take into account the positive or negative charge of that distribution of charges. Yeah, cool.
Okay.
All right, keep going. All right, I think you get better understanding of how to calculate the potential. All right, guys, let's do one more. But now let's try with the one that you don't have any axis or don't have any horizontal or vertical or anything anymore. So this is exactly the same configuration that we did with the electric potential, with the electric field. But now we're going to turn our attention to the calculation of the potential. Say, in the figure, what is the net electric potential at point P? Okay, due to those four particles, if V equal to 0 at infinity, all right, I like this line over here, yeah? Whenever you see this line, it means that is your ticket to use V equal to KQ over R, keeping 0 at infinity. So Q is given to be 5, wow, is it a femto Coulomb? Is it 10 to the negative 15? All right, so you don't need to worry too much about that, okay, because you can look it up, yeah? What is the prefix of all those units there. And the D is also given to be 4 centimeter. All right, guys, let's start. So shall we do the same thing? We kind of like get used to the things that every time that you have charges located at the same distance, the net potential can be found by doing the K, the sum of the Q over A or over R, the distance, right? So we're going to do that again here. Plus Q is at distance D, plus Q is at distance D, minus Q here is at distance D. So at least these three charges can be calculated all at once. So let's do that. The net potential at P is going to be, okay, let me call this 1, 2, and 3. And then we're going to call this number 4. Yeah. So the net potential will be V from 1, V from 2, V from 3, and then V1 from 4. That's the whole concept there. But the first three, they are at the same distance from point P. So we're going to do that all at once. It's going to be K plus Q, that's from the number 1, minus Q, that's from number 2, and plus Q from the number 3. See that? Divided by same distance A. So it's just like I'm pulling the common factor of K over A out. Plus, now what about charge number 4 here? So it's just out here, and the distance is 2D. So it's going to be K, the charge generating that field is negative Q, divided by 2D. Not A, sorry, D. There you go. All right. Nice. So let's work on the first one. These two cancel. So I'm getting positive KQ over D from the first term plus negative KQ over 2D from the second term here. All right. And at the end, that's your final conclusion. Your net potential at YP is going to be positive KQ over 2D. And you are done.
Okay.
You can substitute the numbers or whatever. You can punch the calculator at the end. Cool. I think this is not too bad. Yeah, is my math correct here? Yeah, 1 minus 1/2. Okay, cut positive 1. Okay, so that's a KQ over 2D. Substitute the K, the Q, the D, and then you get the final numbers. Okay, don't forget the unit for the potential is volt. It's in volt. Nice. Any questions so far? All right, if not, now, as promised, we're going to have more calculus for you and even more later. So what if you are facing with this next question here? All right, I want you guys to try first. I'll give you like a couple of minutes head start here to think about how to proceed. The question goes like this. You have find an expression for the electric potential at point P located on the perpendicular central axis of a uniformly charged ring. So you already saw this kind of ring before, okay? And the ring has radius A and the total amount of charge on there is Q. So let me put capital Q there. All right. You did the field calculation from this ring already before. Remember the one that we have the cone, you have to break into vertical and horizontal components. the vertical one just cancel themselves out. I think I can slide back a bit. Oh, it's on the previous slide. So sorry, different handouts there. All right, but anyway, the point is you already found out what was the electric field at P. Now, let's try again with the potential at P, guys. Go ahead. No need that, right? All right, you want to give it a shot? Let's sort of write the first line that you want to attack this problem. Yeah, what would be the first expression that you would need to proceed in the next step? What would be the first thing? What would be the first thing that lead you to the first expression for that? It's calculus. So, I mean, you have to do something by yourself. The charge over here is continuously distributed. So you have to slice this into a tiny piece yourself. And that tiny piece will contain the amount of charge, super tiny dq. Cool. All right, next. What you're thinking of, just like, okay, Dan, what is the contribution of that dq to the potential at point P? We're thinking in the same line over here. So it's going to be just the same formula over there. K, the charge that's generating the potential, dq, over the distance from the charge to the point of calculation. And in this case, it's just from the Pythagorean theorem over there. It's just square root a squared plus x squared. And because this is the potential due to a very like super small charge, we're going to call this dv as well. Why not? Yeah, that's a neat v over here at point P. Now, think about this. You're going to have to keep doing this at other points. So you just slice to the next one. You have another dq, another dq, another dq, another dq, another dq, another dq, another dq. Yeah, on and on. Cool. And you go around this ring until you complete the whole dq on this ring. And that will give you the dv at point P. So every piece of dq on here will contribute dv at point P. You guys with me? However, the good thing is, no matter where your dq is, this expression works perfectly because the distance from any dq on the ring to point P, they are sharing the same distance of root x squared plus a squared. So all you need to do is actually mathematically, you just have to sum them up. That will be your net potential at point P. Cool?
Okay.
However, you have already learned about charges located at the same distance from a point of calculation. You said, well, Ajahn, you have a common factor there. Can you see from the integral over here that you have the same scenario here? Keep going, guys. What's constant? K is constant. What else? That distance square root a squared plus x squared is also constant because the radius of the ring A is constant. The distance from the center of the ring to point P, x, is also constant. There's nothing to do except just the sum of the dq. With me? So they goes pretty much the same line as what you did before with this or with this or with this, same thing. So just pull out the common factor. And then with the rest, you just do the summation of this charge. And you said this is Q. So that's it, guys. K Q over root a squared plus x squared. And you are done.
Okay.
Cool. All right. So I hope you see the potential calculation is a lot easier, right? So, John, why don't you do this kind of calculation first? Too bad, because we wanted to get you to understand the field first. All right. And then we make a connection from the field to the potential. Good thing is potential is just numbers. So you don't have to worry about directions. Nice. Cool. All right. So if this is cool, and now see, you kind of like, it's like, it's, oh, let me have a question here. This one is, no, correct. This is not a vector at all. Potential is not a vector. Okay. And just to confirm, this one is just the energy per unit charge. So energy is never going to be a vector. So that's a good thing. All right. So that's why the calculation of the potential is just the algebraic summation. Okay. Let's make things a lot easier. However, now you have, I hope that up to this point, you see how can you apply the calculus, yeah, stuff, the techniques and everything that you have learned before towards the physics problems and calculations and things like that here. Let's try one more, shall we? All right, still have one more for you. I think up to this point, you should be able to do this one now. Okay, give it a shot. In the figure, let's see if you can do it. In the figure, a plastic rod having a uniformly distributed charge Q, all right, let's say that they already given it to you, and it's been bent to a circular arc. You did this problem already once with the electric field calculation. So that's why I want to redo it again, but for the potential. The radius of the R is given. The central angle is also given. All right, it's supposed to be phi. Sorry, guys. Yeah, that's not theta. Okay. But anyway, that's your central angle over there. With the V equal to 0 at infinity, that's nice. So that means you're going to be able to use the KQ over R. But yeah, you probably start wondering, well, John, and when we are not going to be able to use it, it's pretty much none. They always, I mean, you always use this KQ over R. So, all right, as long as you're not trying to do anything funny about your reference. So, all right, this is fine. What is the electric potential at P, which is the center of the curvature of the rod? What do you think? You need some motivation here, right? No, just kidding. All right, so you say, Ajahn, first step, it looks all right. If you want to apply calculus, you just have to slide a tiny piece of charge, pep, pep, and in here you have dq on it. Cool. Okay, and then of course, this amount of charge will contribute a little bit to the point P. Let me give you sort of like a connection there. So your potential at point P is going to be tiny at this point because it came from K tiny q over R. So that is your tiny potential due to that tiny charge dq at the distance R away from point P. However, you have to do this everywhere. Chomp, chomp, another dq, another dq, 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 dq. You want to go from top to the bottom all the way. But the good thing about this one is you don't have to worry about directions anymore. Second thing is, Ajahn, all of those dq that you slice, they all stay at the distance R away from point P. Does that make sense? So it's going to be quick. All right. So what you need is you just sum all those charges. At the end, you're going to get the net potential at point P. But once again, whatever constant you can pull out, just pull out. K is constant. R is also another constant. So all you need to integrate is just the sum of the dq on this ring, or as you can say is a rod. And what is this, guys? Well, John, this is just, you just add them all. You're going to get back the total charge on this rod. So that's it. So it's going to be K, the whole Q over R, and you are done.
Okay.
Isn't that nice? The angle phi doesn't even come into the picture. I don't care. It doesn't matter. Okay. You can just plug in the numbers and everything. Everything will come down to the volts units. See? So I hope that's sort of like give you a peace of mind saying that, all right, the calculation of the potential, even though it's a calculus based problem, it's not that bad. It's not that bad. All right. So if this is good, keep going, guys. So this is going to be one of the, well, it's the exam level problems. All right. And it's very connected to the previous problem. So I think once you see this one, you see that it's not that bad anymore. Okay, let's take a look at the question. So the length of the rod and the angle doesn't matter. Correct. Because the reason this doesn't matter is just because they said they give you the total amount of charge already. So that is fine. All right. But the length of the rod or the angle will come into your picture if instead of giving you the whole capital Q, they might give you, remember guys, our lambda, the charge per length. Yeah, remember that? The one that we named, or we want the one that we call the density, the charge density. So if instead of giving instead of having the Q given, If you are given the lambda instead, then to get to the capital Q, you have to take the lambda and multiply by the arc length. Does that make sense? Okay, and at that is the time that if you want to get the length of this whole arc over here, then you have to do the r times the phi. That's when the phi will come into the picture. But I think for this one, the problem is very kind to you. It just gave you the total charge already. So bam, just plug in the total charge and then bye-bye, you're done. Cool. All right, very nice. Okay, keep going, guys. So everyone try this one. And I hope that you will see that this one, even though it looks complicated at first, but once you have done a few problems before this one, then I think this one is going to be pretty straightforward and you can get it done in like 2 minutes or something. But at least read it first and say. In the figure, there are three thin plastic rods form quarter circles with a common center of curvature at the origin. So it's just like you just have more than one arc or one bent rod here. That's all. The uniform charges on the rods are given Q1, Q2, and Q3. What is the net electric potential at the origin due to the rods? Can you do it?
No.
Yes.
Okay.
What do you think? Can you see it through that? Oh, John, that's not bad. Because from this previous problem, this or whatever that or whatever this, we already saw that once you have charges at the location where they're sharing the same location among those charges, all you're doing is just K times the total amount of charge divided by the distance, right? You pull out the common factor K over R. Same thing will happen here. So let me sort of like give you the first rod over here. That's one radius. The second rod over there, that will give you another radius. And the third rod over here, that is another radius. That's off. There you go. All right, here we go. Yeah. So, Done. Wait a second. So that means the net potential at the origin is going to be, let me call it like a V1 plus V from the second one plus V from the third, right? That's going to be the contribution from those three rods. But then we already saw it, well, John, the way that you calculate the potential is easy. It's going to be KQ over R right there. It's already got that one. It's like, John, they are sharing the same distance. So let's do it then. So it's going to be KQ1 over, it's 1 centimeter. So let me put 0.01 meter there. Followed by KQ2 over your radius of the second one there, that's just 0.02 meter, plus Q3 divided by, now you have the radius over here, which is 4 centimeter, 0.04 meter. And that's it, guys. You are pretty much done. Is that too easy? And this used to be the question in the exam before, yeah? But for those of you that sort of like forgot about this whole thing, which is like they're trying to do the integral and then they go crazy about it. So even though you try to do the integral, your integral will be super quickly done. It's like, bam, you don't need to integrate anything whatsoever. All right, so you can plug in the Q1, Q2, and Q3. The key is don't forget that every time you do this, the sign is important. Positive, positive, negative. Don't forget to include your positive and negative sign in there all the time. Cool. I think that's not bad. Okay. And I don't know. I hope it's not, they're not canceling to 0 or something. Yeah? Maybe. I don't think so. I don't know. Who knows? That's a possibility there. Okay. All right, guys. Any question up to this point? Sounds good. Looks good. Okay. So if this is good now, all right, almost done, guys. So I think we can finish this handout very easily. So even though we started class a little late, but we should be able to accomplish everything here. Almost, right? So we should be fine. Now, I think I will just take everything and loop everything back into a full circle over here. I already started this lecture, I mean, this topic, talking about the potential energy first. And of course, try to get you to connect with the electric field. Yeah, the fields and the potential energy are related. And then we introduce the potential, which is just a potential per unit charge. Now I'm going to loop everything back. And I'm asking you back about the potential energy one more time and see if you can apply the concepts of the potential and trace back to the energy. Okay, let's look at this. All right. If V at P is given, that's given to be the V sub P there. If Vp is the potential due to the charge Q1 at the point P, then the work required to bring a second charge Q2 from infinity, that's one thing here, that's this sentence again, from infinity to point P is Q2 Vp. You agree with me over this one? One more time. Okay, think logically. At first, the whole universe only contained Q1. There's nothing else, just Q1. Then your task is, well, hey guys, I'm just gonna bring Q2 and place it there. How much work do I need to do? You guys with me? I'm just gonna drag Q2 from wherever it's like so far away, so it's not in the picture at this point. But then I'm just gonna place it there, bam. How much energy do I have to supply to perform this task? See, the good thing about the potential energy is it's path independent. So that means you don't have to care, how do I drag this Q2 into the picture? I can drag in from where, I don't even have to tell you. How did I drag it in? It's just like a straight line, a curve, a zigzag. I don't care. You don't have to know. All you know is you probably start from out of the picture, right? It's not in the picture first. So that's where the infinity is from. That makes sense? You drag the Q2. The Q2 is already waiting for you far away. And you're just gonna drag, I'm gonna put it here. How much energy do you need? Okay, the energy that you need is what? First, the energy, so let me sort of recap. The energy, okay, the work done by the system is going to be how much work you need to do to bring it to point P. So the key is, this is external now, right? This is a work done by me, by me. So it's going to be just the change of the energy. You guys with me? Remember, we discussed last time we sort of like link to the thermodynamics. If you talk about the W of the system, you always have the negative sign in front of the change of the energy all the time of the system. And then you have to switch the role if you are not talking about the work done by the system. If you are talking about the work done by somebody else, you just flip the sign. So now that's why I can start with, if you talk about somebody would like to drag a charge Q2 from infinity to point P, how much energy do I need? I am the external force. I am the external agent. I'm not in the system. And that means I have to calculate the change of the energy. And every time that I do the change, don't forget it's a final minus initial. So it's going to be final total energy at point P, at point P, minus total energy at infinity. Cool? And then we already said the energy is just the charge per unit, energy per unit charge, The potential energy is just the product between the charge times the potential. So that means I can re-express this energy in terms of the Q2 multiplied by the V at P minus Q2 and V at infinity. You guys with me so far?
Okay.
Okay. And then actually, if I want, I can pull out the Q2 for you just to put them in terms of the potential difference between point P and infinity. But we have already agreed with that. with each other, that the potential at infinity disappears pretty much zero. So what you can say is just going to be Q2 times potential at P. Well, Dan, how much is the potential at P? Now you look back over here at P, you only have the potential came from the contribution from Q1 that already sitting there. So V at P is just K Q1 over the distance R12 that's given. So that means what I can just plug it in here is just going to be K Q1 over distance between charge number 1 and number 2. And that's it, guys. Same results over there, and you are done.
Okay.
So you start to see that what's the benefit of knowing the potential. So once again, the concept stays the same. If you want to bring the charge from 1 to 2, from A to B, from I to F, first thing, you just calculate the potential difference between the two first. So you get the delta V, yeah, that will be the potential difference, V final minus V initial, right? That's a potential difference. But then we already understood this one, because if you can figure out the change in the energy, that can be done easily by just multiply through by the charge that you want to move. Does that make sense? Okay, you just multiply through by the charge. Okay, let me move things around a little bit here. You just multiply through by the charge that you are translating. You turn everything into the energy automatically. So this one will be just the delta U. This one will be just the W. Sorry, same thing. I just have to pick one though, right? I don't have to do both, right? So these are just delta U. So this will be the work done by the external force. Done.
Okay.
So let me put parentheses here just to be clear later. All right. So it's kind of like get the whole feeling of what we're doing over here. So the concepts of the potential difference allow us to find the potential energy very easily by just taking the charge that you're moving through that potential difference. You get the potential energy required to move the charge from initial point to a final point. Cool? Plus, the work that we are talking about over here is the work that you have to supply. And that's why in this expression here, the negative sign just disappear, because we already understood back in the day of thermodynamics or previous lecture that if the W is the W of the system itself, you must have a negative sign in the front. I don't know, you sort of like confused about the sign that I'm keep saying like repetitively. However, if you take a look at the example, I hope it will be a little bit easier. Yeah. So I know this is sort of like try to emphasize on, make sure that you understand the expression correctly, make sure that you take into account the correct sign, all that stuff. I know it's boring and it's kind of like, it's like, I don't know, troubling a little bit, but I would like to have you guys sort of like be able to understand this intuitively. So let's take a look at some exercise. Yeah, that will be better. Okay, here, think about this. If the question asks you to say, find the work done bringing 4 microcoulomb charge from infinity to point P, that's simple as it is supposed to be. How much energy do you have to supply to this 4 microcoulomb charge and drag it from infinity to point P? What do you think? So I think intuitively it's going to be pretty simple now. All you have to care about is what is the potential at point P. Does that make sense? So the contribution to the potential at point P, there are 2 contributions here, one from the 5 microcoulomb and the other one from that negative 2 microcoulomb there, right? Okay, so let's start from the 5 microcoulomb. The potential at point P is going to be K, the 5 microcoulomb over the distance from 5 microcoulomb charge to point P, 4 meter. And then you add this to the contribution from the negative 2 microcoulomb. So it's going to be K negative 2, don't forget the negative sign there, divided by the distance, which is 5. So by combining these two, your final result is this. That is your potential at point P. Now here, think about this. See, it's positive. What does it mean by having a positive potential at that point, guys? Potential is higher than the ground. Does that make sense? When you say zero, that's where you are at the ground level. If you go above, that's positive potential. If you go below, that's a negative potential, right? So by calculating V at P at this point, you still have a positive potential. So that means point P having a positive potential. Now you want to drag the 4 microcoulomb charge. You want to drag this 4 microcoulomb charge and place it at point P. So you're dragging a charge uphill. Does that make sense?
Okay.
You go from zero, which is the ground. Zero is at infinity. You want to go up, right? When I say up, because you are going to a higher potential. So you're going uphill. The way that you can go uphill is what? You have to supply energy. So if you want to walk up to the mountain, you have to eat something first, right? Right? You need some energy to walk. So that's what it is. So you have to supply some energy to the charge 4 microcoulomb to bring it uphill. How much? You take the charge, multiply by the potential, and that's it. That is the energy required.
Okay.
Cool. I don't know, does this exercise or this example give you the connections from the potential difference to the energy required to bring the charge to go through those two different potential or not? Right? That's a question comes in. What if you want to drag negative charge? Very good, very good. That's the thing. Because at this point, the charge that you are dragging is positive, right? But if the charge is negative, you're going to get a negative work done. What does it mean by negative work done? It means if you try to bring in the negative charge will love to go there already by itself. So think about it. If the charge is negative, so it means it's trying to get there because negative charge is going to behave opposite to whatever things that positive charge will do. So that means think in terms of the mass, it's going to be the weakest one. Mass go from high to low. Just like positive charge will go from high to low. But once you turn the positive charge into a negative charge, the negative charge will roll uphill by itself. Yeah, so the answer will be for a negative charge, correct. If the charge that you bringing in is a negatively charged, whatever you get is going to be a negative. What does it mean by negative work? It means, think of it like you walking a dog and the dog is trying to go forward and then you have to drag backward. You see what I'm saying? Like, hey, don't go, or something like that. So when the dog is trying to get to whatever it wants to get to, you have to pull that dog backward, but it's still, you are still going forward with the dog, right? So that means you're doing a negative work done. So it's the same thing over here. So if you try to put the negative 4 microcoulomb here, that 4 microcoulomb would love to come here already by itself. So you as an external agent has to exert the force in the opposite direction. So that's why you are performing a negative work, bringing the negatively charged particle at from infinity to point P. So does that answer your whole question here? All right, guys, that's a very good question actually. And that's what it is. So imagine that if point P, on the other hand, is negative, let's say the potential at P is negative, that means the positive charge willing to go downhill because it's like a hole. It's like point P is like a hole already. So the positive charge would love to fall into that hole. So if you want to get the charge there, you just walking the dog as well, right? Because if something would like to go there due to the electric fields and electric force already by itself, you have to sort of like pull back and then slowly get there slowly on, something like that. I don't know my analogy works or not, but that's something that you can relate to. All right, guys, very nice. So that's give you a better clue of how to apply the potential and potential difference calculation toward the calculation of the energy, but they are closely related. It's just simply that extra charge that you are dragging around that just multiplied by the potential difference, you get your energy calculation done. Very simple. Cool. All right, guys, just to test your understanding. Okay. All right. If you can do this one, I'm happy. And it's going to be completely, I would say, the whole picture is being painted. And I think this is good. This is a good place to call it. I have already introduced to you 4 things: charge, I'm sorry, the field, the force, potential, and potential energy. All right. So let's finish this portion with this exercise here. In the rectangle of the figure, the sides have length 5 centimeter and 15 centimeter. Okay, cool. Q1 is given, Q2 is given, V is 0 at infinity as usual. So you're allowed to use KQ over R expression. What is the electric potential at A, the corner A, and B at the corner B? So you just want to figure out what is going to be your potential at A and at B. And now let's do that first. And the sort of like the high point of this is just question C. Okay. So part A, what is the potential at A? Well done, that's easy because you have only a contribution from 2 charges. So it's coming from Q1 and Q2 here. So no big deal. So it's going to be K Q1 over. Now this is 15. So let me put like 0.15, 0.05 here. So that's the length and the height. So it's a K Q1. And then let me put numbers here just to distinguish the 2 sides over here. It's going to be 0.15 down here. Let me omit the unit, yeah, just to save some space here. And you have another contribution from the bottom one. It's a Q2, and the distance is going to be 0.05. Done. That's it. That is for B at A. Now let's move on to at B. So you also have the contribution from only 2 charges here. There you go. All right. So at B, that's not going to be a big deal here. So what you have here is at B, V at B is going to be K Q1. And now the distance over here is 0.05. And keep going. Q2, the distance over there, this is 0.15. So you can substitute the numbers in there, substitute the amount of charge Q1 and Q2 in there, and they're both positive. Is that right? Oh, Q1 is negative. So make sure that you put the sign in there just to be correct. Okay. So make sure that you take into account the sign. So just to be clear, let me do that. So 9 times 10 to the 9. Q1 is negative 5 milli 10 to the negative 3 divided by 0.15. Cool. All right. Plus K times Q2 now is positive 2 milli 10 to the negative 3 divided by 0.05. All right. Because we want to really do this problem. So I'm going to have to work through the numbers, right? Because numbers is important in potential. Positive, negative, 0, everything is crucial. So let me keep doing this. You guys help me a little bit if just in case I made mistakes adding numbers. So let me pull out, what can I do here? That's 3, 6, 1. Okay, that's good. So final numbers are going to be 9 times 10 to the 9, 10 to the negative 3 over 0.15. I think that's what it is. Let me check. No confidence whatsoever, but I hope that's what it is. All right, plus 2. Very good. That's 6 minus 5 is 1. Bottom there's okay. So I think this is correct. And what else can I do? Well, I can work numbers a little bit if I like. It's a 90 over 15 times 10 to, okay, let me do the numbering a little bit, guys. 8 minus 3. And I have another 2 plus 2. Okay, cool. So it's going to be 6 times 10 to the negative 7 volt. Am I right? I hope. 8, 7. Nice. Okay. That's positive, not negative. So, all right. Cool. Let me just put 7 here. All right, guys. So that's what it is. I hope my number is correct. That is the potential at point A. So I'm going to do the same thing with the point B. Okay. I want that number. I want it. So K is always the same, 9 times 10 to the 9. Okay. So I think you guys kind of like get used to this now. Q1 over 0.05. So Q1 is negative 5 micro. So micro is 10 to the negative 3 over 0.05 plus Q2, it's going to be 2 micro over 0.15. There you go. All right, you guys can work on your own and then let's compare notes at the end. So this one is 15. Wow, number is not good. Shoot. All right, but I hope it's fine. So it's 9 times 10 to the 9. Over here, it's 13 over 0.15 times 10 to the negative 3. Already. Okay, the whole point is at point B, the VB, I have the factor 15, sorry, 13 over here. Okay, so that means I know that at point B, my potential is going to, wow, how come it's supposed to be negative though? Oh, my bad, my bad. Sorry, guys. I maybe that's see, I have problem with adding numbers here. It's a negative 8. There you go. It's not whoa, whoa, whoa. No, no, no. I think that is right, but it's negative. All right. So I think 13 is good, but it's negative. All right. Did I do it correctly already? I'm just confused. Okay. All right. So what I see or I'm seeing over here is I just have that extra negative 13 numbers over here. Okay. All right. And the rest of the numbers are exactly as this one right here. So that means I know that at point P is going to be that negative 13 of whatever the potential at A. So, all right, I don't want to work numbers so much, but at least I can tell you it's going to be negative 13 times 6, 10 to the 7 volt. Okay, here we go. Cool.
Okay.
So my work is good, I hope. Okay, let me double check, but I think this is right. Okay, multiply by 3, minus 15 plus 2 is minus 13, and everything else look exactly the same as the V at A. So what I can conclude over here is at point A, I have a positive potential at point A, right there, just to emphasize positive. At point B, I have negative 13 times the potential at A. So potential at B is negative. Cool. All right. So anyway, it's just spend time just working on this. No big deal. All right. But what I want now is part C, guys. Now that's what I want you to answer me. How much work is required to move a charge Q3? So now you have a third charge now from B to A. And I want to move it along the diagonal of this rectangle. You want to give it a shot? How much energy or how much work is required to drag a charge, Q3 charge, from B to A along the diagonal line? How much work is required? It's the same thing as how much energy do you have to supply to Q3 to drag to get it from B to A. Very good, very good. Whatever you're thinking is correct. Part C, the energy or the work required is just, okay, let me put external here, right? Because somebody has to drag it. It's gonna be just Q3 times the potential difference. You guys with me here?
Okay.
Yeah, that's how easy it is. And because you drag from where to where, you have to make sure where you start, where you stop, make sure that you do it correctly or in the correct order. Or what did I do? Okay. You have to do it in correct order. So over here, what you're doing over here is you're going from B to A. So that means your final position is going to be A, your initial position is going to be B. So we have to put VA minus VB, guys.
Okay.
Now, you already figure out VA, you already figure out VB, slap it in, you're done. Cool.
Okay.
See how easy that is. But now let me ask you intuitively before going through like numerical calculations here. Your Q3 is positive. You want to go from B to A. Do you have to do the work? Sorry. Do you have to do the work, or the work that you do by you is negative? You understand what I'm saying here? Do you have to supply the energy to the charge Q3, or you're going to do a negative work done? So this means Q3 is going to roll from B to A by itself, and you have to sort of like walking the dog. What you think is happening? You say, but John, at B, your potential is negative. At A, your potential is positive. You are going uphill. So no doubt, at the end, you're going to get a net positive answer over here. Does that make sense?
Okay.
Yeah, we do the work. Correct. Because it's from B to A, it's uphill. You're going to a higher potential from B to A. So we have to drag the Q3 up. So that means your net work done is supposed to be positive because we're doing the work, supply the energy to the Q3 for the Q3 to have a higher energy at the end. That is the conclusion.
Okay.
Okay. So I hope the reason I keep sort of like making the analogy to the height, the elevation, going uphill, downhill, because that's the easiest way for you to think intuitively. Yeah, it seems to me. Because once you understand the potential, it's no different from potential energy. So whenever you have a lower potential, you try to go up to a higher potential. If the charge that you try to drag is positive, you're going uphill. And if you want to drag a negatively charge, the negative charge do things oppositely to the positive charge. So the negatively charged love to go uphill by itself. So if you want to drag, like in this problem, like an electron, now you walk in the dog. So you're doing a negative work. Cool.
Okay.
That's the conclusion. All right. So I hope that helped. All right. Any questions so far? All right. I know sometimes it's confusing about potential difference. You want to get to calculate the work, and if this is work done by who, by what. See, there is, but I mean, the worst that you probably can do is just you're going to get the sign opposite. That's all. Okay. You shouldn't do, in terms of the numbers, you should get the same result already, but maybe you just got like a positive turn to negative, negative turn to positive, or your interpretation, which is opposite. All right. So in terms of numerical calculation, I don't have any concerns. Maybe it's just your final answer might have opposite sign or opposite explanation. That's all. But once you understood how things goes, just as straightforward as gravitational field and potential energy. All right, guys, looks cool. Now, the last stop of this one, and I think you're going to like this.
Okay.
Welcome to another episode of Vector Calculus. All right. And you have already done integral calculus. Why don't we do some differential calculus? Just change the mood here. All right. However, here's the bad part about this one. I am able to explain how this whole sort of like operation that you're about to face works back in the day of mathematics. All right. However, when I say however means, it's going to take us quite some time to do that. So what I'm going to do is this instead. I think I'm going to roll this whole thing backward, just like before. Okay. And try to give you some impression, the connection between what is this is sort of like giving you when you try to apply this to the electricity theory over here. So let me ask you this instead of, all right, we'll come back to this page for sure, because this is the conclusion that you're going to get. All right. But what I'm going to give you an impression is this. All right. And I don't know, have you seen this before? But if not, then I think this is going to be something that's very useful. Okay. All right. Now, because we talk so much about potential energy, right? And the potential energy that you're familiar with the most is just the mgh. But the h is actually is the y, because that's what you have, the y direction here. You have a mass, you have the height. So the y is just the coordinates. So if you set the ground to be, that's y equal to 0. Yeah, cool. So this is the expression for the gravitational potential. Another thing that you have seen before in the potential energy was the spring, 1/2 kx squared. Okay, this one is x. So that means it's on the horizontal axis already. So you can have a mass on a spring. Okay, and then you might have like somewhere to be your equilibrium point. That's when x equal to 0. So the x give you the expansion or contraction, or I mean the stretch or compressed location of the spring. Okay, and then you can evaluate, or you can determine the potential energy by doing the 1/2 kx squared, given the k to be the spring constant. Okay, and of course back in here you're given the g to be your gravitational acceleration. Cool. So what's the point here, John? All right, so what I'm going to show you is this. I don't know, have you done this before? First, look at the gravity. Let me put the subscript g here just to signify this is gravity. Give me the derivative of the u sub g with respect to y. Let's do that, shall we? So I'm going to do du by dy. What do you get? Well, John, I get mj. That's easy differentiation. I'm going to do the same thing with the spring. I'm just going to do the derivative of the spring potential energy with respect to the coordinate x. What do you get? Oh, x squared, the derivative is 2x. 2 cancel with the 1/2 there. So you're going to get kx. Do you feel something now? Does this look sort of like, Adan, that's something here. There is something to it here. Now, the mg, if you turn this into a vector, well, Adan, I know there is an mg pointing down, and that is the gravitational force. So what I'm saying over here is, if I put the negative sign in the front of that derivative of the ug differentiated with respect to u, I will be able to get to this mg pointing down. Is a negative here. So that means I can put a j hat here. You remember our j hat? That's unit vector. And this will give you the negative mg as what we like. That showcase that, hey, guys, this is the force that's doing behind the scene work of the gravitational potential energy. It's the gravitational force, mg, pointing down. Let me do the same thing here, guys. Here. Well, hey, Dan, if you take the negative into this one, and you put the coordinates here, because we differentiate with respect to x, this is going to be the I hat here. But wait, Dan, I'm kind of familiar with that. F equal to negative kx is the Hooke's law. Whoa, that's cool. Wow. So what you have over here is you get the negative kx I hat. And that is your restoring force from the spring. The same thing as we study in oscillations, right? You're going to have exam next week, yeah? So, whoa, Dan. So that means, isn't this a way that you can go from your potential energy, yeah, down to the force behind it? See, you have potential here. You can go down to the force behind it. And the operation that we just did, what do? We take the energy, potential energy form, doing the derivative with the coordinates system. And whatever you got, you put the negative sign in the front, and that coordinate will suggest the unit vector. That's my way of writing it.
Okay.
So that's what it is. Because we saw the close connection between the field and the potential, we already knew going uphill, that's mean higher potential, going downhill, that's mean lower potential. So when we talk about electric field, You go up the field, that higher electric potential. When you go down the field, that is lower electric potential. Concepts are the same. So that means if you already had the way that you can connect between the force and the potential energy in this form, why don't we have that here? Oh, yeah. Can you see it now? So what we can do is from now on, if you already got the potential, just take the derivative with the coordinates, put the negative sign in front, you will get the force in that particular direction. Cool. So I'm going to show you what is done here. All right. So here we go. I need another page here. So what I'm going to do is this. And just give me one more. Oops, sorry, wrong one. I don't know why can't it be like a default of the landscape mode. I have to keep swapping this all the time. All right. So now here we go. So if I have the electric potential energy, but because now back in this day, gravity is always pointing down. Spring, you already put in a one dimension. So usually you put it either in the X or in the Y, doesn't matter, but it's a single dimension. But back in here, potential energy from the electric charges can be anywhere. It can put, it can be anything. So the key is you usually will be given as a function of coordinates other than just single coordinates. You can have multiple coordinates factor into it. It could be in under function of X, function of Y, function of Z. It doesn't matter because you can already see that the potential looks crazy. Yeah. So let's say somehow you are given a function of potential energy. How can we figure out the force behind this? Well, Ajahn, it's going to be very easy. You just take the derivative of this. However, it's a 3 variable problems. So you have to do it one at a time. So what I can do is I can do the derivative with respect to X. But now because you want to do just only along the X axis, you do the partial derivative. Here we go, guys. Partial derivative. That's no big deal. The partial derivative is just the derivative with respect to just a single coordinates there. And then you put the negative sign into it. That will give you the force along the X. You are done.
Okay.
Isn't that cool? And then you just keep doing this. But again, what about the force along the Y? You take the U, differentiate with respect to Y, slap in the negative sign, bam, you're done. And what about the Z component of this? You take the derivative of U with respect to Z, slap in the negative sign, bam, you're done. That's it.
Okay.
That's how simple things are. Seriously. But then we have a trick. It's not a trick. We have the connections between the force and the field, and we have the connection between the potential and the potential energy. Remind you again, F equal to QE, and energy is just QV, yeah? It's just a factor of Q, the charge. So what you can do is I can just write F as the charge multiplied by the E. I can write the U as the charge multiplied by the V. You see where I'm going here, right? And eventually Q will cancel. So that means, of course, think in your head, if the charge that you're talking about is 1 coulomb, just like your friend's comments, your test charge is 1 coulomb, or let's say you want to get rid of the think of everything per unit charge. Energy per unit charge is going to be your potential. Force per unit charge is going to be your electric field. So that's why what I can do is this. Now you can figure out the electric field along the X component to be just a negative of the potential with respect to X. Done. You can keep going for the Y component. You take the derivative of the potential along the Y. Put the negative sign into it. Bam, you're done. The C component is a negative potential along the Z, slap in the negative sign. Bam. That's how you connect the potential function and the electric field function. So instead of giving you the function that representing the energy, you might be given the V as some function of X, Y, and Z. And once you are given that, you can figure out electric field vector through this expression right here. And you are done.
Okay.
Isn't that cool? So all of the impression that I try to sort of like lead you to into this is just do the comparison with these two form of the potential difference. Sorry, the potential energy that we have already familiar with. And we say that, okay, by just taking the derivatives, you can get down to the force that's underlying those potential energy easily. Take the derivative with respect to the coordinates in the function, slap in the negative sign, that will give you the vector components along that coordinates. So we're going to apply that here. But then because we can have potential that's going in crazy in all three coordinates, so that's why you can have the electric field in all coordinates. So you do the partial derivative with respect to each component in your coordinates. You do derivative with respect to x, slap in the negative sign, you get the x components. You do the derivative with respect to y, slap in the negative sign, you get the y components. You do the derivative with respect to z, slap in the negative sign, you get the z components. And I hope that gives you this here. And you are done, guys.
Okay.
I hope this is easier for you to grab onto this expression through the comparison. For some of you that has already done some vector calculus, you might be able to look into this through another perspective of just like you think of it like a total differential. And I just split this into the product, the dot product between two components vectors. And then we can rearrange that, relate this one to the concepts or the definition of the potential difference. But to me, given that, I mean, even though this derivation is very proper and you utilize the definition of the potential difference, but just for this problem alone, I mean, it's just so easy for you to just take a look at this one and just be happy with the comparison with these two, I hope. That's my take on it. I don't know. All right. Anyway, but for those of you that want to dig a little bit deeper, just study this. I think this is a good place. I mean, this is a good things that if you really want to dig a little bit deeper and if you understand this one, it will be very nice. Okay. But it seems like I just try to do something that's more obvious. Okay, that's a question comes in X, Y, and Z represents V in X, Y, and Z directions, right? Okay, don't forget that V is a scalar quantity. So there's no direction yet in the V. The function here is just a scalar function. Cool? But then you extract the information of the vector out of scalar quantity. Isn't that cool?
Okay.
Make sense? All right. So let me do this. I think your question, I think it's come in the right direction. I have one final connections that I want to make, but let's do one example first, shall we? And then I think my conclusion statement will answer your question exactly. Okay, here we go, guys. So the question of this one is like, even though you don't understand anything at all, you will be able to do this. Seriously, because you just follow the process. Think of this like a cooking recipe or something. Like, okay, hey guys, look at this. You are given an electric potential function. See, it's in the function of X, Y, and Z, blah, blah, blah. And then they're just asking you about, hey, calculate electric field from the electric potential given. Right. So I'm showing you here. It's a recipe. You want the X components of the electric field. You can find it from take the derivative of V with respect to X and slap in the negative sign. So it's going to be negative. Here we go, guys. Still remember how to do the partial derivative, yeah? When you do the partial derivative with respect to X, you treat Y and Z to be just numbers. So that's going to be 2xy plus 0, yeah, because y cubed is just numbers, plus z. Cool? That's it. Believe it or not. That's just the x components of the electric field. Keep going, guys. Y component, do the dv by dy, negative. First one, you get x squared. Second term, you get 3y squared and 0 on the third. And that's it, guys. It's a negative, or I forgot here. This is supposed to be negative here. Okay, let me put it here like that. Okay, negative x squared plus 3y squared. See, done. And the last one, just do dv by dz. Negative is there. First term is gone. Second term is gone. Last term is x. So this is negative x. And that's it, guys.
Okay.
When I say that's it, what does it mean? From here, if, what is the electric field vector at 1, 1, 1, for example, just for fun? Okay. So what you need to do is just plug in x, y, and z into all these three expressions here. That's all I need to do. So I'll show you what it is. So it's going to be this. It's going to be negative. Let me plug in 1, 1, 1 there. That's going to be 3. You guys with me? Yeah. And this is going to be in the I direction. That's the x components. Plus the second term is going to be negative. And 1, 1 there is going to be 4. And that's along the j. Okay, let me write the notation nicely here. Negative 3 there. Okay. And the last one, you just plug in the 1, 1, 1, that's minus 1 from the x there, and it's k. And that's it. You are done.
Okay.
So that means just from the starting point of the function of the potential, this will allow you to calculate electric field at any point. Any point, seriously. And that's it. You will know exactly at 1, 1, 1, you will have an electric field pointing along this, along that, along here in 3-dimension space. Cool. All right. So I think that, as I said, the recipe is there. It's easy to do. That allow you to calculate electric fields given the electric potential function. But what does this actually mean, guys? Okay. So, okay, this final one, you can look it up a little bit later, but that's okay. So what I want to add at the end is this, guys. I hope this will give you the connections one more time. Okay. If we think in terms of the 2D, let's do V only like 2-dimension. Make it simple a little bit. So it's going to be some function of x and y. Okay. And every time that we plot something in x, y, you need 3-dimensional. So it's going to give you a surface. Does that make sense? This is f of x, y. And you take f of x, y to be the z-axis, right? That's the way it goes. But then if you want to draw the whole function on the xy plane, well, Dan, I don't want to do the surface drawing and stuff. I want to do everything on an xy plane. What do? The way that you do it like this. Well, the way that you do it, well, Dan, you set this to be 0. Once you set into this one to a 0, you get a function of x and y, right? And then you move on to 1, you move on to 2, you move on to 3, you move on to 4. So that means you just pick the value of the function. When you pick the value, it means you just do the slicing. That's x equal to 0, and then do another slice. X equal to 1, you do another slice. X equal to 2. Does that make sense? So it's just like you have a surface, but then you sort of slice that surface out one layer at a time. But then each layer of you will cut through your surface, and it will give you the shape of the function. Does that make sense? Yeah. Each layer will cut through your surface. You will get a line out of it. So at the end, what you're getting is you're going to get something like this. I hope this will look familiar to you. Maybe. Woohoo. Woo. Something like that. And then you probably say, okay, Dan, this is like 1, 2, 3, 4, 5, 6, 7. Does that give you any clue? Yeah, it's sort of like it's a contour map, or it's an elevation map. It's a map. It's a heat map telling you how high it is, how low it is by using just the 2D pictures or 2D plotting. So it's a contour map. So if you think of this to be just like a geographic plotting, give you elevation. So the numbers that you're supposed to put on here is going to go opposite. Think of it like that here. This is like the top of the mountain. It could be like 1,000 meters above the sea level. And this could be like 900 level, 800 level, 700, 600, 5, on and on, right? So that means if I'm standing here, I am at the top of the mountain here. Woo! Right there. Now, let me ask you this, guys. If I want to go downhill and I want to go in this direction, which way will be the quickest way that I roll downhill, guys? Well, and of course, you just go down straight. When I say straight, what does it mean? I have to cut through this contour in a perpendicular fashion. You guys sort of get the intuitive sense of this one? Because if I want to go downhill the quickest, I want to go to the direction that is the steepest. Whichever direction that give me the steepest, I'm gonna go that route, and that will be my quickest way to get down to the ground or whatever. On the other hand, if I start in this corner over here, I'm gonna go downhill the quickest. I have to go this direction here. If I go in this direction, I have to go here, cut through it perpendicularly, cut here, cut there, and cut here. So I'm gonna have to walk this way. See, when I say I walk that way, so at any point, the direction of my walk is always perpendicular to the contour map. See that? Contour, contour, perpendicular, perpendicular, perpendicular. So now you see where I'm at. So what is the perpendicular to the line or to the contour? That's exactly what we have in our field theory. Yes? You got that kind of idea here? Yes? Yeah, come again. Come back here. See? MG is pointing down. My upper screen over here, that's my, let's say, 1 meter high. I can cut through this to be one layer of mine. And the bottom of the screen, that is, let's say, that's my 0 height. To go from 1 meter down to 0 meter, the quickest way is just go straight down, straight down. That's the quickest. And what is the direction of the straight down? That's where the G is pointing. So the G is connecting between two surface, two level, 1 meter and 0 level in the quickest direction. That's the G. And at its perpendicular. Does that make sense?
Okay.
Okay, so that's the whole point. So the whole point is, we already saw this. Every time that you saw the electric field, we said that we just cut through the field perpendicularly to get to the same potential level. So now we do it backward. If you have the potential level, what will be the direction of the E? You have to cut through perpendicularly as well. Those are the interchange role between the two. If you have the field to get to the potential, you have to cut the field perpendicularly. So back way, I mean, the way backward is going to be the same thing. If you start from the potential, if you want to get back to the vector, you have to cut those contour perpendicularly as well. Come back here. Our Coulomb's law. We already said here, KQ over R. To get to the field, to see each concentric circle over there have the same center, right, at the charge. But if you want to get to the field by having those blue dash line to be your contour representing this KQ over R, to get back to the vector, perpendicular, 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 everywhere. To get back to the field, cut the contour perpendicularly, you get the field. And the operation that allow you to do that, coming from the scalar function to the vector, is just this operation right here, and you are done.
Okay.
Does that answer your question here? All right, so the key, just answer your comment in the chat there, just saying that the V is the scalar function. And you create the vector out of your scalar function by doing this operation here. And you get a vector that always points perpendicular to the contour map or the level map of that function here. Cool. All right, guys. So I'm just over time a little bit. Sorry, guys. I started late today. But I hope you go back and revise it a couple of times. I hope you will see the connections that I'm trying to make over here. And if you still have questions, we still have next time I'm going to show you the last exercise that just have your brain absorb this one a little bit, and next time we will review one more time. And I hope it was stuck in your head a little bit better. That sounds good. All right, guys. Thank you for sticking around, and I'll see you guys next week. All right. Bye bye. Any questions?
Okay.